So, it's not rocket science, but you can see from the subtitle, well, actually it is. But this is an attempt to explain the basics of rocket science, meaning orbital mechanics and how spacecraft get between planets, but without the maths.
What do you do?
Well, I don't mean to boast, but I'm a brain surgeon.
Brain surgery? Oh, it's actually rocket science.
And this talk is not about rocket technology, it's not about rocket engineering, it's not about how you build one of these things, it's basically how you get it to go where you want it to go. Not in terms of purely liftoff, but how you get from planet Earth to Mars or Jupiter or somewhere else. So I'll be talking about what a rocket is for, talking about orbits, about how Kepler discovered elliptical orbits and Newton explained them, about how you get from A to B in the solar system, and how you use gravity assist to get from one planet to another with the minimum amount of fuel, and then what sort of started this idea of writing a talk about rocket science was a question I got a long time ago, is how can the James Webb Space Telescope park at a particular point in space called a Lagrange point? So it'll finish with what these parking spots are all about. So, is rocket science complicated? Well, I like this quote. That's why I love rocket science. It might seem very complicated at first, but when you dig deeper, you soon realize it's even more complicated. And I like that sort of quote. So let's start with rocket science. What's the purpose of a rocket? If you ask this to many people, most people will say the purpose of a rocket is to go vertically up and get an object above the atmosphere. Well, sort of, but not quite. Because when you think about it, the International Space Station and the Hubble Space Telescope, for instance, are in orbit around the Earth, but they're still in the atmosphere. It's just that the air is rather thin at an altitude of 500 or so kilometers. To put an object into Earth orbit, it's not the vertical speed you need, it's horizontal speed. That's all you need to go into orbit. Getting as high as possible is usually a good idea because you want to reduce the amount of atmospheric drag, but strictly speaking, it's not necessary. You can, in principle, go into orbit at any height above a gravitating body. Newton knew this. We've known about this for 300 years. This is not new. The insert in the top left there is Newton's Principia, and it's blown up as a big cartoon on the right here. And the idea is if you put a cannon on top of a reasonably high mountain and fire the cannon out horizontally, in the usual sense, meaning parallel to the horizon, then if you don't fire it very fast, it'll fall to Earth, indicated by A, and if you fire it a little bit faster, it'll fall to Earth, but it'll go further, point B. And if you fire it fast enough, it might be possible to go in orbit around the Earth. And if you had a planet with a much stronger gravity, you would need to send that cannonball out even faster to go into orbit. So in other words, if you want to stay in orbit at a given height above a planet, you need to go fast. And the stronger the gravity, the faster you need to kick that object in order to get it to go around the planet and stay in orbit. So this idea of horizontal velocity is not a new idea, but everybody thinks about rockets as they're designed to go up, because that's what rockets do when they first leave the Earth. And here's an example. Initially vertical, but after a little while, it's not long before it tilts over. That's not an accident of perspective. That's what rockets actually do. Once they've got above the ground, they start to lean over because it's the horizontal velocity that you need to go into orbit. Yes, you want to lift them a reasonable number of kilometers into the air, but it's the horizontal velocity that matters. If you don't have horizontal velocity, for instance, Blue Origin's New Shepard, if you take a rocket and go vertically up, what happens when you get to the top and you switch the rocket off? Well, you fall straight back down again. If you don't have horizontal velocity, you don't go into orbit. So New Shepard went to an altitude of about 100 kilometers or so, the definition of space if you wish, but in 10 minutes it just came straight back down again. So it's always the horizontal velocity that you need, and that's what effectively defines various orbital mechanics. So an orbit is defined as the path of an object affected by essentially only gravity. In other words, once you've switched off your rocket motors, the path you then take is called an orbit. An orbit doesn't have to be a closed circle or a closed ellipse. It can be an open path, which we'll see later. So we're all used to the idea that planets go around the sun in something close to circles. Okay, they actually might be ellipses rather than circles, but we're used to the idea of planets going around the sun and moons going around planets. And Kepler observed that the planets orbit in ellipses, and then he passed that data on, and Newton figured out why planets move in ellipses, because of the universal law of gravitation. And we tend to think of the orbits as being so-called conic sections. If we take a cone and slice through the cone at various angles, we see various shapes: circles or ellipses or parabola or hyperbola. And these are essentially the shapes that dictate how objects move around the sun. And here we can see that if we imagine the yellow dot is the sun, we can see circles and different ellipses of different so-called eccentricity, and also parabola and hyperbola. And these various shapes that define the curves of orbits around the sun are also the same shapes that define mirrors that are suitable for focusing light. And the reason for that is because the maths is basically the same, and so you get the same set of solutions. We've just said planets follow closed elliptical orbits around the sun, and if an object falls into the solar system from way out in the outskirts of the solar system, from the Oort cloud, for instance, a large cloud of icy bodies, then the object will follow something very close to a parabola, shown here in red. If an object comes into our solar system moving at speed rather than being dropped from zero velocity into the solar system, if it enters the solar system at speed, then it will follow a so-called hyperbolic path. And then it will leave the solar system because it will have more than the solar system's escape velocity. And that indeed happened a little while ago. The object, this asteroid came into our solar system in 2017, and we observed it coming into the inner part of the solar system. It didn't get particularly close to Earth, but we observed it and noted its speed, and from its speed as it goes past the sun, we can work out how fast it must have been traveling as it entered our solar system, and we can calculate that it will have enough speed to leave the solar system. Now, in terms of orbits, there's only really one basic concept that you need to understand orbital mechanics. The details are, well, the devil is in the detail, but the basic idea is relatively straightforward to get your head around. Imagine we have two planets going around the sun. The green planet is closer to the sun, so its gravitational pull is stronger. Remember the cannonballs on top of the mountain? If you've got strong gravity, you need to go fast in order to stay in orbit. So the green planet is being pulled quite strongly towards the sun, and it moves quite fast to stay in orbit. But the red planet is further from the sun, so its gravitational pull is less, and so the planet moves more slowly to stay in orbit. Let's just imagine they're circular for convenience here. And so it has a longer period, or year, if you like. And so let me just run that again. That is the key observation that is really all you need in orbital mechanics. Stronger gravitational pull means that the object goes faster to stay in orbit. That concept, close to the sun means strong gravity means you move faster, explains pretty much all you need to know about rocket science, arguably. If we see that in action, here's a little cartoon of what's going on around the Earth. Very close to the Earth, there are lots of objects going around, like the space station and the Hubble, very close to the Earth. Much further out, we have things like the Global Positioning System satellites, with an orbital period of about 12 hours. And much further out, we have this outer ring, which is objects that are moving around in a 24-hour orbit, the geostationary orbit. And you can see that the further out we go, in terms of either kilometers or miles, the slower we are going. Very fast, close to Earth, much slower as we get further and further away from the Earth. And that's true, of course, of the planets. When we actually look at how fast the planets are moving, how long they take to go around the sun compared to their distance from the sun, let's just assume again they're circular for the time being. If we plot out distance from the sun on the horizontal axis and the orbital period, how long it takes them to go around the sun in Earth years, then we find that all the planets know everything there is to know about Newton's law of gravity, and they sit on that line quite nicely. Just another point to make regarding how objects move. If we think about two equal masses, they could rotate about their common center of gravity. They don't need to have, for instance, a star in the middle. We can think of planets or perhaps two stars moving around their common center of gravity, the red cross in the middle there. If the two objects are different masses, then the center of mass is closer to the large body, and the large body then moves less than the lighter body, the smaller body. So the center of mass now is here, closer to the larger mass. And we take that to a little more extreme. If the masses are very different, the center of mass might actually be inside one of the two bodies themselves. For instance, the Earth and the Moon, the center of mass of the Earth and the Moon, about which both rotate, is actually inside the Earth. And if we take that to the extreme, even a small object like a planet can make a larger object like a star wobble. And that's how exoplanets can be detected. We can't necessarily see the exoplanet, but because it's having this effect on the star, if we look at the spectrum of the star and look at the Doppler shift, the shifting to the red or blue end of the spectrum, we can see how much that star is moving, and we can infer the existence of an exoplanet simply by looking at the spectra of a star, even though we can't see the planet itself. So that idea is very useful for exoplanet detection. Now, the relative motion of two objects is absolutely calculable. But unfortunately, physicists have to admit that when it comes to three objects, well, we can work out how they move by doing simulations, but there are no analytic solutions for how three bodies move. So for instance, if we take three objects, at first it looks like, oh, they're just doing nice ellipses. So that's nice, just like a two-body problem. But no, the more we watch it, the more we realize they're not actually falling into nice elliptical motion. They are chaotic. In other words, we can run simulations, but we cannot work out analytic solutions to this problem of what do we do when there are three objects all gravitationally attracting each other. So when it comes to actually modeling, for instance, the solar system, we can't do it analytically. We have to resort to numerical simulations. So how do we actually get, for instance, from the Earth? Let's assume we've got a rocket to get us, roughly speaking, above the Earth's atmosphere, and we've got enough horizontal velocity to leave the Earth. But how do we get, for instance, from Earth to Mars, or how do we get to the rest of the solar system? Well, here's an example of a little graphic that shows how the spacecraft called InSight left Earth back in 2018 and went to Mars. We don't necessarily wait until Earth and Mars are as close as they can be. We want Mars to be a little bit ahead of the Earth, because if it leaves Earth here, it won't arrive at Mars until we're on the other side of the solar system. And we can see that in this little simulation. The purple shows the path of the spacecraft. In order not to use fuel, we try and follow an orbit which is the most efficient possible. So although in principle we could get to Mars faster by waiting until Mars was really close to the Earth and then going hell for leather as quickly as possible, that would use a huge amount of fuel. Whereas if we do it in this particular mode, we find it's the most energy efficient way of doing it. One thing to notice is that as the spacecraft approaches Mars, notice that it's slightly ahead of Mars, and Mars is actually catching it up. Mars is actually going faster than the spacecraft when the spacecraft arrives at Mars. So what you have to do when you get to the Mars orbit is you have to catch up with Mars, because it's going faster than you are. One way of looking at that is to take it schematically and look down from above, as it were. Let's just get rid of some of the extraneous detail for the moment. If we imagine we're traveling from a circular orbit, which is Earth's, to a circular orbit, which is Mars, if we leave Earth at this point, we aim to arrive at Mars when Mars is on the diametrically opposite side of the solar system. So again, that's perhaps not quite intuitive, but that's the most energy efficient way of getting there. If we follow an orbit, which is this blue orbit, let's just temporarily get rid of the other two, this blue orbit, this ellipse that intercepts the Earth and Mars, the home planet and the destination, is a so-called Hohmann transfer. And it's the easiest way of getting from A to B within the solar system without using any other means. So what we actually do is accelerate the rocket. In other words, we give it a delta V. Virtually all of rocketry is based on how much do you need to accelerate, how much do you need to increase the velocity of the spacecraft that you're trying to shift. So you give the rocket burn enough to give you a delta V to give you a kick to get out of Earth's orbit and put you onto the blue line. So you can see the blue line is going outside the green circle, so that means you need an acceleration to get onto the blue curve. But remember, when you reach Mars, Mars is actually going faster than you are. So you actually need to give another kick, another delta V, to get into orbit, to actually follow Mars at the same speed and ultimately go into orbit around Mars if you so wish. If you didn't give that kick, you would continue following the blue curve and you would come back down here to Earth. Well, strictly speaking, you'd come back down to Earth orbit because it would take you about a year and a half to follow the blue curve. But of course, in a year and a half, the Earth will have gone from that point back to the same point again in a year's time. And in a year and a half, the Earth won't be in the same place. So if you follow the blue line and decide not to land on Mars, but to come home again, you come home to Earth's orbit and Earth isn't there anymore. That is one of the reasons why going to Mars is so difficult, and that's one of the reasons going to Mars is something like a 2-year mission. You can't simply go there, spend 5 minutes there, and then come home again because the planets aren't in the right place to do that. So Hohmann is a particular method of getting from A to B that is fuel efficient, but you have to wait until the planets are in the right place in the solar system in order to decide when you're going to launch and when you're going to arrive. But what about getting to other planets in the solar system other than our immediate neighbor, Mars? In the 1960s, it was realized that if you want to fly to the outer part of the solar system, it's a good idea to slingshot past other objects. In other words, get a so-called gravity assist from other planets as you go towards the outer solar system. And it was realized in the 1960s that there will be a fortuitous alignment of planets in the 1970s that would allow exploration of these outer planets. So that means that you can get to the outer planets faster and you can get there cheaper and use yet less fuel. So you have more instruments rather than lots of fuel to get you up to high speeds to explore the outer solar system. In effect, what's happening is the spacecraft robs the planets of some of their momentum, and the planets lose a little bit of speed and the spacecraft gains a little bit of speed. But how can that be? If we think about an analog, let's not think about planets, let's just think about an object rolling down a hill. There's a hill and a valley and another hill. And if that object is static there, we give it a little bit of a push, it then builds up speed, it accelerates down, it has a maximum speed at the bottom of the valley, and then it decelerates as it climbs the hill the other side, and it ends up back at the top of the other hill if it's the same height. And that's the key point, the same height. At any point in that trajectory, if we look at the object at the same height, it has the same speed. In other words, whatever speed it gains on the way down, it loses on the way up. And of course, we're assuming no friction, no air resistance, nothing like that. And in fact, that's such a universal law, it doesn't actually matter what the shape of this hill and valley is. It can be as bumpy or as odd or asymmetrical as you like. It will always be the case that once you reach the same height, you must have the same speed by so-called energy conservation. So if that's the case, how on earth can we gain anything by slingshotting past a planet like Jupiter, for instance? If we think about this max speed down here, we can say, well, we haven't got a hill anymore, but we are falling into the gravity well of Jupiter, for instance. So the max speed at the closest point to Jupiter would be the max flyby speed. But from what we've just said, won't it be the case that if we have some inward speed on the way into Jupiter and some outward speed on the way out of Jupiter, from what we've just said, whatever you gain by falling towards Jupiter, you're going to lose again by coming out away from Jupiter. And whatever you gain on the way in, you will lose on the way out. So how is it worth it doing a slingshot past a planet? Somebody figured out that there's a particular catch. The speed in and the speed out are indeed the same as seen by Jupiter. In other words, Jupiter sees an object coming in at a particular speed, and Jupiter sees it leaving at the same speed. But Jupiter itself is not static. Jupiter is trogging along because it's going around the sun, and it's going around the sun with a considerable velocity. So if the speeds relative to Jupiter are the same, if you can arrange it that the object leaves in the same direction that Jupiter is moving, then it gains all of the speed that Jupiter had. And if you do that right, when you're coming in, you might come in at 10 kilometers per second, but if you arrange the geometry right, you might leave Jupiter at something more like 25 kilometers per second. There can be a substantial gain, and these, of course, are speeds relative to the sun. The speeds relative to Jupiter are the same, but the speeds relative to the sun can be very different, and that's how you gain speed by by slingshotting past the planets on your way to the outer part of the solar system. So they tried this in the early 70s. They took Pioneer 10, they left the Earth in 1972 and went to Jupiter, took a few pictures of Jupiter and slingshotted round it. Not because they needed the velocity per se, but that just seemed like a sensible thing to do to try out this whole maneuver. And also it meant that Pioneer 10 gained enough speed to actually be thrown out of the solar system. So it was a way of taking pictures of Jupiter as well as having a probe leave the solar system, which could then report back on what the outer solar system was like in terms of its properties. So that was done with Pioneer 10 back in the early 70s, and that was followed very soon after by another idea. Let's do the same again, but this time let's slingshot past Jupiter and use Jupiter's, there you see the slingshot, you see the change of trajectory is quite extreme. It does a 90-degree turn to the left effectively, and it slingshots it right across the solar system to pick up Saturn some years later. And in this particular case, it got quite close to Saturn and again had an extra slingshot from there. Some years later, they decided to do this as full as they can, the full grand tour. Voyager 1 left in 1977 and was sent past Jupiter. Again, a trajectory that takes it close to Jupiter, and then a kink in its trajectory shows you that it slingshotted past Jupiter, picked up some extra speed, and was sent then on its way to Saturn. Notice when it passes Saturn, no slingshot. There was no particular need to slingshot and gain speed when it passed Saturn. The primary aim of this particular maneuver was to actually look at Titan. They wanted to have a close look at Titan, and so they didn't go close to the planet to pick up speed. They went on a trajectory that took it past Titan. When Voyager 2 came along, which was a few days behind it basically, they knew that Voyager 1 had already taken pictures of taken pictures of Titan. So there was no need to go past Titan a second time, which means Voyager 2 had the option of slingshotting past Jupiter and slingshotting past Saturn, to hell with Titan, slingshot from Saturn, and then you notice that you then have this beautiful alignment of Uranus and Neptune that allows you to explore essentially the entire outer solar system in one go with the minimum of fuel. That particular slingshot maneuver past Jupiter and then slingshotting from Saturn, there's very little to be gained when you slingshot past Uranus, and again, if you look at the kink here, there's almost nothing to be gained by going past Neptune, but it's already fast enough to leave the solar system, so if there's no more planets to explore, there's no need for any more slingshot maneuvers. If we actually look at the speed of Voyager 2 relative to the Sun, here we've got distance from the Sun in astronomical units, multiples of the distance from the Earth to the Sun, and here we have speed relative to the Sun in kilometers per second. So it started from Earth at a distance by definition of 1 astronomical unit up there in the top, and as time went by, as distance from the Sun increased, the velocity of Voyager changed dramatically. You can see that each time you go past a planet, the velocity spikes quite considerably. It dropped towards Jupiter, then we got a huge boost at Jupiter, then another boost at Saturn, and smaller boosts. And in fact, there's a little bit of a drop as we pass Neptune. We're not fussed about increasing our velocity any further. If we look at what velocity do we need to leave the solar system, that's the blue line. So as Voyager approached Jupiter, it didn't have enough velocity to leave the solar system. It had enough velocity to make it to Jupiter. But by slingshotting past Jupiter, its speed goes up, and thereafter the red line is always above the blue line. So from that point onwards, regardless of whether you do the slingshots or not, you have a speed that's required to leave the solar system. So the slingshots were to get you to a Uranus faster and to pass the various moons that you wanted to photograph on your way in to those planetary systems. The idea of using slingshots, using gravity assists between planets in the outer solar system seems perfectly reasonable. But actually, it's used for the inner solar system as well. For instance, there's currently a spacecraft on the way to Mercury, and on the way, it's flown past the Earth to get a gravity assist, and then it's flown past Venus to get a gravity assist, and then it's flown past Venus a second time to get another gravity assist. That was in August of 21. And it's now flying past Mercury multiple times to get multiple gravity assists. It's not trying to gain speed, it's trying to lose speed. Instead of arranging it so that you leave the planetary system in the same direction that the planet is moving, if you arrange it the other way round so that you leave it in the opposite direction to the way the planet is moving, you end up losing speed and the planet gains speed rather than the other way round. So if you were to drop into the solar system straight from Earth to Mercury, you would be going way, way, way too fast. So the idea of a planetary flyby, each time here, the spacecraft loses speed, and the bottom line is, regardless of whether you're accelerating or decelerating, the reason you use gravity assist is because you don't need to use fuel. You don't have to take fuel with you to accelerate or decelerate. You use the solar system that's there to actually allow you to gain or lose speed by just swapping momentum with the planets. There are times when you do need to use fuel. For instance, when Cassini went to Saturn back in 2004, 2017, it wanted to go round Saturn and take pictures of Saturn from various angles. So that was its orbit around Saturn. It's a very complicated orbit, and in order to keep changing from one ellipse to another ellipse, it had to keep firing its thrusters, it had to keep using fuel, because if you want to change orbit when you're sitting around a planet, you basically need to keep firing those thrusters. And of course, if you take fuel with you, that's a certain mass. That means you've got less mass for your instrumentation, and it reduces the mission lifetime. You've got to take enough fuel with you to last as long as you want the spacecraft to operate. And this indeed was an issue regarding the James Webb Space Telescope. How much fuel are you going to take to produce enough maneuvering thrusters effectively to allow you to operate for 5 years or 10 years or more? That's a calculation that they always have to do. So let's finish with this fourth element of how do you actually park at a point in space where there's nothing actually there, these so-called Lagrange points. And we return to this basic idea. Everything is based on this idea that if you're closer to the sun, you move faster. If you're further from the sun with a smaller amount of gravitational pull, then you can move slower and stay in orbit. And we can understand Lagrange points without the maths, simply with that basic idea. So here, for instance, we're just schematically showing that the green planet is pulled quite strongly towards the sun, but the red planet, being further away, is pulled slightly more weakly towards the sun. So greater distance, the force is less. The question is that always the case? Well, yes, if we only consider the planet being pulled towards the sun. We can't change the gravitational pull of the sun, but we can arrange it so that one object is not only pulled towards the sun, but is pulled towards something else, an additional gravitational force. So let's imagine that the green is planet Earth and the red is some object that we want to, it's either a spacecraft or an object that's also in orbit around the sun, but not in orbit around the Earth. So green is the Earth, and green goes around the sun in 1 year. The red orbit is larger, so it has a period of more than 1 year. If it was a long way away, it would be like Mars, and it would have an orbit of something like 2 years. But what if the red orbit is close enough, so this isn't necessarily to scale, what if the red was only slightly outside the green orbit, so that the red object is close enough so that it's pulled not only by the sun, but also pulled by the Earth? So an object there in the red orbit still is pulled to the sun, but there's now an additional, rather weaker pull towards the Earth itself. And remember, the red and the green orbits are relatively close together. It is possible, we're not going to do the maths, but it is possible to find a red object that's just at the right distance from the Earth, such that the red object is pulled towards the sun and pulled towards the Earth, and that means it ends up going faster with a period of 1 year. Remember, stronger gravitational pull means things move faster. So because it's now being pulled towards the sun and the Earth, it's now moving faster. So instead of having a period of more than a year, it now has a period of 1 year. So if the red object has a period of 1 year, what does that mean? It goes round at the same rate as the Earth. It goes round in 1 year. The red object is always being pulled towards the sun, but the Earth is always in the same direction as the sun. So the red object is being pulled and also goes round in 1 year. So in terms of what it looks like, as far as the Earth is concerned, it looks like that point in space is always up there. It's always there on the opposite side of the sun. It's always sitting there like a parking spot waiting to have a spacecraft parked at it. And that's really all Lagrange points are. This particular one I've described is a particular Lagrange point. This point here, if we morph into the labeling of Lagrange points, this is what we call L2. L2 is a point in space such that it's being pulled towards the sun and being pulled towards the Earth such that it goes round with the Earth. It's not orbiting the Earth, it's orbiting the sun at the same rate as the Earth, one orbit in 1 year. Now, it's definitely not to scale because the distance from the Earth to the sun is 1 astronomical unit by definition, and the distance from L2 to the Earth is only something like 1/100th of that, so quite definitely not to scale. So that distance, to put it into context, is about 4 times further than the moon. So the distance from the Earth to L2 is about 4 times as large as the distance from Earth to Earth's moon. L1 is the same basic idea. We don't have to do the same argument all over again, but L1 is in an orbit inside that of Earth. So you'd expect L1 to go round faster. But because it's being pulled towards the sun in one direction and towards the Earth in the opposite direction, the total pull on L1 is less. And if it's got less gravitational pull, it goes round more slowly. And therefore, L1 goes round the sun in 1 year. So again, the Earth to the sun is 1 astronomical unit, and L1, approximately speaking, is about 1/100th of that inside the Earth's orbit. So L1 is a great place to park a spacecraft if you want to observe the sun. The Earth never gets in the way. If you had a spacecraft orbiting the Earth and you wanted to study the sun, you'd have to worry about the fact that every once in a while the Earth would get in the way. By putting a spacecraft at L1, the sun is always visible. The Earth is always behind you, if you like to think of it that way. So yes, we can calculate where these Lagrange points are. We know that the gravitational force between 2 objects falls away as the square of their distance. So it's straightforward enough. All we have to do is write down the formula for the mass of the sun, the mass of the Earth, and there it is, and we just solve for R. Simple. But yes, I do admit that the first screen did say it's not that hard if you just skip the maths, so we are going to just skip the maths. But in principle, that's all we need to do. Knowing that gravity falls off as 1 over r squared, we can calculate where L1 and L2 are. There are other Lagrange points. There are other places where we can park things. There's another point on the opposite side of the sun called L3. We've never actually sent a spacecraft there because it's not very useful. Yes, it views the other side of the sun, which might be interesting, but it can never tell us what it sees because it's always hidden behind the sun. So we've never sent a spacecraft to L3. We have used L1 to park spacecraft, such as those that are observing the sun. And the more famous one, as of the last few months, is L2, because that's where spacecraft like Gaia and the James Webb Space Telescope are sitting. Why do you want to sit at L2? Well, the main reason for wanting to sit at L2 is that if you build yourself a sun shield, you'll block out the light from the moon and from the Earth and from the sun all at the same time. You don't have to worry about the moon and the Earth and the sun being in different parts of the sky and having to shield yourself from the light or the heat if you're worried about taking infrared measurements, as in the case of the James Webb. You don't have to worry about trying to shield the light from these 3 objects, which are effectively light pollution as far as an orbiting spacecraft is concerned. So by going to L2, you can build yourself a sun shield and then block the light from those 3 objects, and essentially look out into space unimpeded from the glaring effects of those 3 bodies getting in the way. Technically, L2 is actually in Earth's shadow because it's on the line from the sun to the Earth to L2. It's in eclipse, effectively. The Earth eclipses L2. And so Gaia and James Webb Space Telescope don't sit actually at the L2 point. They move in little orbits around L2 to keep them in the sunshine, which means their solar panels still charge up and they get electrical power. What happens if an object moves slightly away from L2? Well, if it moves away in the sense of this diagram in the downward sense, well, the Earth is pulling it back up again because there's a component of the Earth's pull which is partly pulling it towards the Earth and partly pulling it upwards. So if the object drifts away in the downward sense, it gets pulled back towards the L2 point. And similarly, if it drifts away in the upward sense of this diagram, it gets pulled back towards the Earth again. The catch is that if it drifts in the left-right sense, according to this diagram, if it drifts towards the Earth, it'll get pulled more strongly towards the Earth, which means it drifts faster towards the Earth, which means it gets faster and faster and faster. In other words, if it drifts towards or away from the Earth, it doesn't self-correct. The other two directions, it always self-corrects, but in these two directions, it doesn't. If a spacecraft moves towards or away from the Earth, then it will continue to drift in that direction unless you do something about it. And we can see the dynamics of how it works by this particular sort of contour plot, if you like. We can see how it is possible to park at a Lagrange point if we calculate these contours and think about an object that wants to roll downhill, and we think of these contours as being, if you like, height above sea level. So if we imagine a ball wanting to roll downhill, let's look more closely at L2 to see what that tells us about what's going on around L2. So these contours, high in the top left, high in the bottom left, and lower as we get closer and closer to Earth. But this is the point we're interested in, L1. And if we think about which way is downhill, if we're going from high to low, we can see downhill points towards L2 in the sense of up and down in this diagram, but points away from L2 in the sense of left and right. If we point towards the Earth, that's downhill. We're going to continue rolling downhill to the Earth. So L2 is not a hilltop, in which case downhill would always point away from the hilltop. L2 is not a gravitational well. If it was, the arrows would always point towards L2. But some of them point towards, some of them point away. So L2 is not a hilltop, it's not a gravity well, it's a saddle point. Mathematicians would express it like that. The rest of us would just say it's a Pringle. So the takeaway message is the James Webb Space Telescope is sitting on a Pringle, because in one direction it wants to run downhill, in the other direction it just wants to come back to where it started from. So that means that you can take a spacecraft and you can put it in a so-called halo orbit, a little orbit as shown by the little circle there. And if it goes up and down, that's fine, because the downhill is always bringing it back and stopping it from going anywhere. But if it drifted towards the Earth, it would continue drifting towards the Earth. And therefore, it would need a station-keeping nudge every once in a while. So that's what they've done. They haven't put the James Webb Space Telescope at L2. They've put it in an orbit just on the Earth side of L2, so that very slowly it drifts towards Earth. And every few months, they're going to fire the thrusters and push it back to L2. And then it will drift slowly towards Earth, and every few months, they'll give it a small nudge, and it'll put it back to L2. What they cannot afford to do is push it too far. If they pushed it too far, it goes over this saddle point and starts drifting away from Earth. And if it starts drifting away from Earth, they cannot push it back again, because there are no thrusters on this side of James Webb Space Telescope, on the right-hand side, on the cold side of the James Webb Space Telescope, there are no thrusters. They don't want any thrusters that contaminate the optics. So the thrusters are on the left-hand side, the hot side of the sun shield. So if they drift to the left, they can just push it back again. But if they pushed it too far, they would have no choice but to either continue letting it drift or to turn it upside down to fire it back towards Earth. But that would expose all of the sensitive instruments to sunlight, which means the very nice cold spectrometers that they now have would all warm up again. So that's why they were very, very, very careful about sending the James Webb to the L2 point with the intention of just arriving ever so slightly short of L2, and then they will continue with these maneuvers every few months. Because that particular placing of the James Webb was so accurate, they saved a lot of fuel, and so this station-keeping nudge that they'll need to do every few months, instead of lasting for 5 years or 10 years, is hoped to last for more than 10 years and keep it in position around L2 for more than a decade. That's the intention. What about 4 and 5? Well, we haven't placed spacecraft at 4 and 5, L4 and L5, but there are things there. For instance, the L4 and L5 Lagrange points of the Jupiter orbit does have some asteroids. If we again come back to our sort of donut to get an idea of what's going on, there are orbits that objects can have around the L4 and the L5 point. But there's not much there in the Earth's orbit, simply because the Earth isn't a particularly large object and the gravity isn't really strong enough to hold any objects around L4 and L5. But Jupiter is a large enough planet such that some objects have collected over the billions of years of the solar system's history. Some objects have collected in these particular regions, the so-called Trojan asteroids, not necessarily that large, but effectively small bits of debris from the solar system have been caught by Jupiter's gravity and held at these Lagrange points, which are, in a sense, parking spots for asteroids. They will move a little bit away from L4 and L5 and drift away, but generally speaking, they will always come back again and hover around the L4, L5 point. One point to finish on is that some orbits look really, really weird. We're used to the idea that orbits are circles or perhaps ellipses, but some orbits are distinctly not either of those two. That particular orbit looks really, really weird. It's actually following one of the contours of this shape, so it's not going either uphill nor downhill. And that's the direction that an object might move. But it still obeys the rules. In other words, when closer to the sun, the object goes faster than the Earth. So if we imagine an object up here, as well as going around the sun, it's getting pulled because it's getting a little bit closer to the Earth. If it's getting pulled towards the Earth, it tends to come down and closer to the sun. If it's closer to the sun, it's now going faster than the Earth because it's got a stronger gravitational pull. And as the Earth goes around the sun, this object is going faster. So this gets further and further and further ahead of the Earth until eventually it catches up with the Earth on the other side. And now what's the Earth doing? The Earth is now pulling it up and out. And now it gets to an orbit which is further away from the sun, which means it's moving more slowly. So it starts lagging behind the Earth, and it starts lagging more and more and more behind the Earth until eventually it comes back to where it started from. So this horseshoe orbit looks really weird. It doesn't look quite so bad when you remember that this whole thing is rotating at the rate of 1 revolution per year in the case of the Earth. L1, L2, L3, L4, L5 are not static points in space. They are static relative to the Earth. And remember, the whole system is rotating. So even though that horseshoe orbit looks really weird, it does actually obey the rules of when you get closer to the sun, you move faster. When you get further from the sun, you move more slowly. And there are orbits that are not even closed orbits. Most of us can just about accept the fact that, yes, objects move in circles or ellipses. But if you were to take 3 objects and position them just so, you end up with a system that looks like this. There is no reason why they have to close. In this case, the objects come to a rest, and then gravity pulls them back again, and they follow exactly the same trajectories backwards and forwards. If nothing else got in the way, these 3 objects would continue to follow the red line, the green line, and the blue line forever. And that's just from 1 over r squared. But you have to place them at just the right place in order for them to follow that particular pattern, as it were, or orbits. They are orbits, although we tend to use the word orbit when thinking about closed orbits rather than open orbits. So is it possible for 3 stars in a triple star system to move that way rather than the conventional way of orbiting around each other? Well, in principle, yes, but they'd have to start from precisely the right place. And it's difficult to see how that could possibly happen by chance. So we don't think open orbits like that will ever describe the way stars or planets ever move. And don't get me started on black holes, because black holes, the space around a black hole is so distorted, then Newton's ideas of universal gravity means that we'll end up with ellipses and circles doesn't apply anymore, because space is just completely messed up by the black hole at the center. And that simulation gives us an idea of what an object might try and do in the vicinity of a black hole. So I've told you a little bit about orbits. The reason, if you're wondering about Buzz Aldrin, is Kepler observed orbits, Newton explained orbits, and Buzz Aldrin seems to have an innate ability to see orbits and calculate in his head. Most people would rely on a computer to tell you, how do I rendezvous from this orbit to that orbit? Buzz Aldrin seemed to have the capability of working it out in his head. His PhD was on orbital mechanics of rendezvous, so perhaps that's not so surprising. I've told you a little bit about how you can get from A to B, Earth to Mars, and gravity assists. What these parking places are all about, although they sound a bit weird, Lagrange points are simply a result of the fundamental relationship between if gravity is strong, things move fast, if gravity is weak, things move less fast. So why is rocket science considered to be so hard? Yes, there are definitely some objects in the solar system that move in ways that are not at first sight very intuitive. And yes, calculating how to put the James Webb Space Telescope into orbit around L2 was not a trivial thing to do, especially given the phenomenal accuracy that they actually achieved in getting it where they wanted it to be. But the underlying ideas behind rocket science are straightforward enough. Stronger gravitational pull leads to faster motion. Its simplest analogy is, yep, the Earth moves around the sun faster than Mars. You apply that to any other situation, you can understand most aspects of orbital mechanics. That's really all there is to rocket science. The rest, the detail, is just the maths. After all, it's not rocket science. Thank you all for listening.